Welcome to today's lesson. In this first tutorial, we will solve absolute value inequalities and graph the solution set. So we're still in section 1.7, but now we're going to focus our attention on absolute value inequalities. But before I do that, I'd like to look at a visual on this number line. So here's our big number line. Of course, right here in the middle of our number line is the number 0. So I'll go ahead and put 0 here. We have positive numbers to the right of 0, and we have negative numbers to the left of 0. What I'd like to do first is put some red dots 3 units away from 0. So I'll grab the first red dot, and let's go 3 units away from 0. So 1, 2, 3, naturally we would go to the right to the number 3, and that red dot is exactly 3 units away from 0. But we still have one more red dot, because there is one more location that is 3 units from 0, and it could be to the left, 1, 2, 3. So we could put 3 units, or excuse me, put the red dot that's 3 units to the left of 0, and this is what your graph would look like for an absolute value equation. If we had the absolute value of x is equal to 3, then our solution set would have two answers, and those would be positive 3 and negative 3, but only those two numbers. What I'd like to look at next is what happens when we're looking for numbers that are less than 3 units away from 0. And that's what I'm going to do in blue. So if you have a different color, you could use a different color. I'm using blue. So less than 3 units from 0, well, right there at 0, that's less than 3 units from 0. 1 would be less than 3 units from 0. 2 would be less than 3 units from 0. I still have plenty of blue dots here. How about negative 1? That's still less than 3 units. And negative 2, that's less than 3 units. I still have plenty of dots here. So what am I going to do now? How about I go in the middle? That's less than 3 units. That's negative 1/2. Here's positive 1/2. How about negative 1.5? How about positive 1.5? How about negative 2.5? And how about positive 2.5? And of course, every other number in between. This represents all of the infinite numbers that are in between negative 3 and positive 3, and that is what the graph would look like for an absolute value inequality. The absolute value of x is less than 3. When you're talking about an absolute value inequality where it is less than, then you're going to be talking about a range of numbers that is in between two other numbers, a shaded in between. And I like to think of the less than symbol as, I call it a less than symbol, because this is going to be an and sentence, meaning that it's these answers and another set of answers, and it's an intersection. So that's all the numbers that would be less than 3 units from 0. Now let's talk about all the numbers that would be greater than 3 units away from 0, and that's what I have in green. So of course 4 would be greater than 3 units, and 5, and how about everything in between? How about 3.5, and how about 4.5, and how about 5.5, and of course all the way up to infinity. Let's go on the left side. Negative 4, negative 5, negative 3.5, negative 4.5, negative 5.5, and of course everything down to negative infinity. We can see that there are two ranges of numbers that are greater than 3 units from 0. There's this outside on the right set, and there's this side on the left side set. And this is the solution, what the graph would look like for an absolute value which is greater than a number. And what I like to think of this as, it's the absolute value of x is greater than 3. I like to think of that as a greater symbol, because this is an or. Now I understand that I'm misspelling the word greater. I'm treating it as greater as kind of like a mnemonic device to help me to remember that when I see an absolute value that is greater than, it's an or statement, meaning that it's not an intersection. It's this set of answers or this set of answers, and the graph will always look like that. So that's just a nice little warm-up to see the difference between an equation, which would only have two answers, and inequalities, which has shaded answers. The ands would be shaded in between, and the ors are shaded on the outsides. So that's a nice little start. So let's start solving some of our inequalities. We're going to use the same process that we did last lesson with our absolute value equations. We're going to do the same exact setup. Our first step is to make sure that our absolute value bars are isolated, that they are all by themselves, which this one is. So therefore, I can go ahead and start solving. But before I do that, I look at this less than symbol and I say, okay, that's a less than symbol. This is ultimately going to be an and answer, meaning that our graph is going to look like shaded in between two numbers. So let's see if we can go find those two numbers. Now I can split up into two different absolute values. The first one is exactly what I see without the absolute value bars. So 2x plus 7 is less than 11. The other one is going to be the opposite of that 2x plus 7 is less than 11. That's exactly what we did with our equations, and it's exactly what we're going to do today with our inequalities. Write the statement without the absolute value bars, and then take the opposite of the absolute value expression, less than 11. Nothing else changes. And now we have these two inequalities. The only thing we have to watch out for is when we multiply or divide by a negative. So I'm going to subtract 7. I'll solve this first one here. And I've got 2x. Subtraction does not change my symbol. 11 minus 7 is 4. And now I will divide by 2. Dividing by a positive number does not change my symbol, and I get x is less than 2. Okay, great. Now I could distribute this negative, or I could just divide this negative away. In this case, I'm going to divide this negative away. When I divide by a negative, of course, it cancels out this negative, and I'm left with 2x plus 7. Dividing by a negative number will switch my symbol to become a greater than. And of course, we have negative 11 here. So watch out when you multiply or divide by a negative number. Now I'll subtract 7. Basically the same exact steps that I did over here now. 2x, subtraction does not change my symbol. This is negative 18. And I'll divide by 2. Dividing by a positive does not change my symbol, and I get negative 9. So I'm talking about all the answers that are less than 2 and all the answers that are greater than negative 9. That is my set of answers. Now I can write it a little bit cleaner than that. When it's an and statement, that means that x is in between two numbers. So I can write x in between the two numbers. I know that we're greater than negative 9. So here's x is greater than negative 9. And that we're less than 2. So here's x is less than 2. That is a much nicer way of writing these answers. If it's an and, we can put the x in between these two numbers. And it makes a whole lot more sense now to graph our answers. The negative 9 I'll put on my number line right here. The positive 2 I'll put on my number line right here. You don't have to go crazy with putting all your other tick marks in the middle. I do need to understand that this is strictly a greater than symbol. If I'm reading from the x, of course, I'm reading this way. So that means it is an open dot. I'm not including the negative 9. And this is strictly less than 2. So that's an open dot as well. We're not including, but we're shading everything in between because this is an and statement. And that's how we solve that. Our second inequality, well, we can't go split anything up yet because it's not isolated. This negative 5 should not be here. We need to divide the negative 5 away first. So let's get rid of that negative 5. Then I will have my absolute value bars all by themselves. Watch out, negative 5. When we divide by a negative, that's going to switch that symbol, and now it's going to become a greater than or equal to. Negative 40 divided by negative 5, of course, is 8. And now once it's isolated, I can use my little mnemonic trick to say, ooh, it's a greater than symbol. This is an or. And in the end, I know that my graph is going to have, a number here and then shaded above that number and then another number here shaded below because that's what all or graphs will look like. So let's see if we can split this up into our two inequalities. The first one is exactly what we would read without the absolute value bars. Nothing changes there except the brick bars go off. And the next one is the opposite of the 3x minus 2 is greater than or equal to 8. So that's how we split up our two inequalities for an OR statement. Same way all three times. Equations, less thans, greater thans, always the same way. So let's solve each one of these inequalities now. We have 3x is greater than or equal to, adding does not change my symbol. This becomes a 10. When I divide by 3, I'm not scared of fractions. That's okay. You're going to get fractions. I get 10 thirds. I'll just leave it as 10 thirds. As long as it's reduced, we're fine. The second one, I think I'm going to divide that negative one away. So I can cancel that away, and I'm left with the 3x minus 2. This time, since dividing by a negative, is going to switch this to a less than or equal to, and I've got a negative 8. And then I go and I do my two more steps. I add 2, and I've got 3x is less than or equal to, what is that, it's negative 6. And then I'll divide by 3, and that feels a little bit nicer because it's divisible. Negative 6 divided by 3 is negative 2. And I make sure that I put my big word or in there. Now there is no convenient way of writing these. We have to write them as two separate ones. We don't get the luxury of writing the x in between two numbers because an or statement is not that. The negative 2 would come here, and the 10 thirds would be over here. Because these include the values, they're the or equal to parts, I can put closed dots on each one of these. And now look where we're shading. Everything less than or equal to negative 2 would be this way, which we knew would be the case. And I'm going to shade the arrow in to show that it goes on forever that way. And x is greater than or equal to 10 thirds would shade this way. And like I said, all OR graphs would be shaded like this, where we're going in the opposite directions, so I know that I have that correct. I think I'm going to come back here and make a nice little note here to remind ourselves that we must isolate first. We cannot solve absolute value equations or inequalities until our absolute value bars are isolated first. So that's a good note. Let's look at examples 3 and 4. These are actually our special cases, and these should not take much work at all. The first thing I'm noticing is that the absolute value bars are isolated. It is simply all by itself the absolute value of 6x minus 1. But I'm seeing that I'm looking at a negative 7 here. And I know that absolute value can never equal negative, but these are not equations. I'm talking about less than negative 7, and over here I'm talking about greater than negative 7. Well, let's use our logic. If absolute value can never be equal to negative, the absolute value of something can never be equal to a negative, could it possibly be less than a negative? If it can never equal a negative, then it makes sense that it would never be less than a negative. Never less than a negative. Hopefully that makes sense to you. If it can never equal a negative, there's no way that it could be less than a negative. So if we were trying to solve this, it wouldn't even make any sense. The absolute value of something can never be less than a negative. So our answer is null set. There are no answers. If we tried to graph that, well, there's nothing to graph. I'll just put a null set symbol on top of the graph. We cannot solve this. Conversely, if we're talking about absolute value greater than negative 7, well, that will always be true. Absolute value will always be greater. Well, I'm not going to say be greater. Always greater than negative. So that means that it doesn't matter what we put in here for x. The absolute value of whatever this expression is going to be will always be greater than -7. The smallest that this could possibly be is 0, and 0 is still greater than -7. So that means that the answer to this is the set of all real numbers. And if we wanted to graph that, well, geez, I guess we'd be graphing the entire number line because everything works. So these are our special cases, and you want to pay attention to these. Once you've isolated your absolute value, let's see if we have a negative value over here. If it's equal to, we know that that can never happen. If it's less than a negative, we know that that can never happen. If it's greater than a negative, we know that that will always happen, and the answer would be all reals. So those are two special cases. Pay attention to those. No, I have two more. Let's see what we can do with this. Here's a, oops, I've got a 2 out here. I need to isolate my absolute value, so let's first divide by 2. And then I'll have the absolute value of 4x plus 5. Dividing by a positive does not change my symbol, and this becomes a 13. Do we have an and statement, or do we have an or statement? Once it's isolated, I see a greater than symbol, or, a greater symbol. So I'm going to split this up, and it's going to be two separate numbers with an or in between. So the 4x plus 5 is greater than 13. I'll just write that exactly how I see it without the absolute value bars. Or the opposite of the 4x plus 5 is greater than the 13. Those are my two statements. And now let's solve. We'll subtract 5. And I have 4x is greater than 8. Divide by 4. Whew. Nowhere along this way did I divide by a negative, so it stays a greater than symbol, and here's greater than 2. Let's see what we can do with this one. Maybe this time, just to practice, I'm going to distribute the negative. If you like dividing the negative away, that's fine. Just don't forget to change your symbol. I'm going to distribute it this time and see what that looks like. So there's a minus 4x and a minus 5. And then I'm going to add 5. And I have my negative 4x. Adding doesn't change my symbol. Here's an 18. And now I will divide by negative 4. Now watch out. Instead of dividing with a negative at the beginning, now I'm dividing by a negative at the end. Now it's going to change my symbol to a less than symbol. And 18 fourths, it's a negative, I know. 18 fourths reduces to 9 halves. You could put 4.5, I guess, if you would like, but understand that this is a negative. And I'll put my or in the middle, and here are my answers. Go ahead and circle that, and let's graph. So make sure you put the numbers where they're supposed to be. 2, of course, would be on the right side. Negative 9 halves would be on the left side. This is strictly greater than. This is strictly less than. These are open dots. Greater than 2, I shade above. Greater than 2 would be to the right of 2. Less than negative 9 halves would be to the left. I'll shade below. And that's the graph of my answers. That's what an or statement would look like. So now in our last example, example 6, let's isolate our absolute value by subtracting 4. And we will have the absolute value of x minus 2 is less than or equal to 6. This is a less than symbol, so I know I'm going to end up with an and statement and an and graph in the end. So now let's set up our, break apart our two things. We've got x minus 2 is less than or equal to 6. And we have the opposite of x minus 2 is less than or equal to 6 as well. And now let's solve each one of these. We've done these plenty of times by now, so I'm going to go a little bit faster. And it looks like we have less than or equal to 8. I'm going to divide by my negative 1, and I will have x minus 2. That flips the symbol, of course, to a greater than or equal to, and there's negative 6. And when I add 2 to both sides, I will have x is greater than or equal to negative 4. So these are my two inequalities separated by an and. Actually, I'm not going to circle them this time. Since it is an and, I should be able to write together the x's in between my two values. My smaller value goes on the left, my greater value goes on the right, the x is in the middle, and notice that my inequality symbols are all increasing from the -4 to the 8. So that is the best way to write my answers to an and. And then it's easy to put my little -4 here and my +8. Since we have the or equal to part, they're both going to be closed dots. And since, of course, the x is in between these two values, our answers are in between these two values, and there is our graph. Thanks for watching this tutorial, these 6 examples, and we'll practice this more in class, and I will see you in the next part of the tutorial. Thanks for watching. See ya.